So my name is DuToit. Michael McCool is currently traveling, so he couldn't be here. So I'm here instead. I'm going to talk about it's actually a commercial product that's developed out of years of research here at the University of Waterloo that's still ongoing, called the RapidMind development platform, and in particular about how this applies to image processing. So RapidMind is a company, a startup company in Waterloo. We're at about 13 people right now. It's built on top of years of research that Professor McCool did here at the University of Waterloo in the computer graphics lab. It started off as a way to program GPUs. So GPUs are graphics processing units. They're chips which are enormously powerful, located on every video card in every computer, basically. And around the end of around the late 90s, early part of this century, GPUs started surfacing which had programmability built in. So you could actually start programming these GPUs to do things other than display graphics for games or the types of things they were targeted at back then. Michael McCool headed an effort to build a programming language for these GPUs and explore what kinds of programming paradigms might make sense for these. This eventually led to a prototype by about 2001. We continued doing research on this system and ended up incorporating a company in 2004, which closed a round of VC financing earlier this year. So what's so exciting about this? Why are we doing this? Traditional CPUs like Intel Pentiums, AMD processors, and so forth are relatively serial processors. In the last couple of years, they haven't really been living up to the increases in performance that we used to expect from CPUs. So over here, I've got a graph. Down at the bottom is actually the peak gigaflops rate. And I apologize, this only goes to about 2004, but it continues about the same shape. For an Intel Pentium 4 processor, and this is doing floating point operations. So as you can see, we still get some speed increases, but they're not significant. The red and green lines are ATI and NVIDIA GPU peak gigaflops rates. So these processors can be used for general floating point computation, and you can actually achieve on current hardware about 30 times the amount of floating point power that you can on a conventional CPU. Much more significantly, GPUs are growing at about 3 times the rate in terms of processing power every year that CPUs are. And this is expected to continue for a while. So what makes GPUs special is that they're not serial processors. They're highly parallel processors from the ground up. They exploit parallelism in many ways, and this allows them to take advantage of area on chip much better. There are other processors that are starting to evolve in this direction. The IBM Cell processor has been getting a lot of attention. It's the main processor in the next Sony PlayStation 3 console. It follows a similar architecture to the GPU, although it's not focused on graphics per se. It's more of a general purpose processor, but has a highly parallel 9-core design, which with very fast floating point power processing support. Intel and AMD, of course, are looking into multi-core CPUs, so they're trying to leverage parallelism by basically adding more cores to a system. Intel also has a research project called Terascale, where they're thinking about processors with hundreds of cores, as well as similar sort of vector processors to GPUs. And we have another example, which is the AGEA physics processing unit, which recently launched and also has a very similar design to the Cell processor. And we think these processors are going to find their way into all areas of computing. In the short term, these processors are going to find their way into areas where particularly large amounts of computation are necessary in a particularly short amount of time. So what's the problem with these processors is that they are not traditional CPUs. We cannot use traditional programming languages like C++ in a standard fashion and expect them to run well on these processors. You might be able to port them, but they're not going to be able to exploit the parallelism inherent in these processors, because these processors really rely on the compiler and the optimizer and the person developing the application to write their application in a parallel fashion from the ground up. So trying to solve that programmability issue is what we're doing. RapidMind is the name of the company, and also the RapidMind development platform is our solution. The way we've developed our solution is we decided not to build a special purpose language. Instead, we've built something into C++, using a standard C++ library, essentially, that pretends to be a language within C++. So developers continue to write their programs in standard C++. They use, normal compilers and so forth. At runtime, we go and collect operations which they expect to execute in a parallel fashion, and stream those to whatever processing elements may be in the system. So whether it's a multi-core CPU, an IBM cell, or a GPU, or some other kind of parallel processor. The way that people use our system is they find the components of their application that they really need to accelerate. This is usually, for a lot of people, this is a fairly obvious place. There's usually one inner loop that's very heavy duty. They replace the types that they use for numerical computation there. So instead of using standard C++ float types, they use our types, which are called values. At that point, everything they do with these values is captured, compiled at runtime, and streamed in a parallel way to these CPUs. And all of this execution is managed by us. So I have a quick code example here of an image process, very basic image processing technique, convolution. So we take an image. The system has built-in support for arrays. All of the bold types are types which are contained in our system. So it's an RGB image with 1024 by 1024 values. We take a 3 by 3 filter. When we declare a program there on the third line, we're saying, start collecting operations. I'm going to execute everything between begin and end on my GPU or my multi-core CPU or so forth. We declare the inputs to our program, do the computation. Down here, we take our image, shift it repeatedly to get neighbor access, feed that into the program, and finally take the result of the computation. At this point, our computation will be executed in parallel across whatever cores you have in the system, and run in a highly efficient manner. And at this point, you can run the computation over and over again with different images and so forth. So if you want more information, it's at rapidmind.net. I realize this is a very short time to explain a programming language, but feel free to ask questions. And I can show a video in the meantime if you'd like.
So you're actually then selling this as an adjunct to normal Pentium processors that can be added into a system doing imaging-related processing? Is that the idea?
Yeah, it's a software product that you install. You use it while developing your applications if you're developing in C++. And then we sell, it contains several backends for different systems. So that includes GPU backends, which can run on graphics processing units for general purpose computation, not just graphical computation, as well as a backend for the IBM cell processor, which we are also developing.
Question?
Do you guys make a compiler for MATLAB?
We've thought about integration with MATLAB a little. Yes, exactly. So is our language. C++ is not, but the types that we add to C++ are vectorized. It would certainly be possible to make a MATLAB front end that would then work through our system to generate code that runs on these processors, and that's a very interesting and intriguing idea. Yeah. Well, come talk to me afterwards.
Richard.
Another thing that's interesting is that even on Pentium-type CPUs, the floating point unit is highly pipelined.
Yes.
So if you write a C++ program, it'll run probably 5 times slower than if you do that same thing in MATLAB, because the MATLAB is vectorized. Right? So you just take 1,000 by 1,000 matrices, multiply by another 1,000 by 1,000 matrices, take the result time, wall clock time. It'll be like 2.5 clock cycles on Pentium 3, and it'll be 15 clock cycles on C++. There's some potential even for taking that middle code in C++ and pipeline
Yes.
on even on a Pentium back.
Yes, and we've certainly thought about making a highly optimized CPU backend as well. Right now, the reason we're focused on GPUs is, I mean, that'll get you optimal CPU performance. Optimal GPU performance is an order of magnitude higher.
But it would be nice to have
Something that,
a feature that somebody could take an existing C++ program and where their bottlenecks are. They don't reprogram it or pipeline it or anything. Where their bottlenecks are, just work on it. And they could get 5 times performance increase.
Right.
50 times by going.
yes, exactly, yes.
Other questions?
And,
If not, thank you very much. Appreciate your comment.
thank you.